Hi Chem students, it's Ms. Horn and welcome to a lesson over atomic structure. This is chapter 3 in your textbook. So the atom. The atom is the smallest particle of an element that retains the properties of that element. So in the bottom left I have a picture of a piece of carbon and you can see its physical properties. But on the right I have a diagram of the carbon atom where you can see the components that make it up. Speaking of those components, they're called subatomic particles, like the electron, proton, and neutron. There are some symbols that we use to abbreviate the particle whenever we don't want to write the whole thing out. So you may see me write E- for electron, P+ for proton, and N0 for neutron. These also show the charges of those particles. Electrons are -1, protons +1, and neutrons are neutral. They have no charge. When comparing the masses of these particles, you can see here that the proton and the neutron are very similar in mass. They're the heavier particles. But looking at the electron, it's much smaller than both of these. As you see in the diagram, the electron cloud is where we find electrons, and the nucleus is made up of the proton and the neutron in the center of the atom. So when comparing protons and electrons, we said the weight is much different. So here's an example. If an electron weighed the same as a dime, a proton would weigh the same as a gallon of milk. So there's a very big difference there. Although their masses are different, their charges are of the same magnitude. So like we said earlier, the charge of an electron is -1 and the charge of a proton is +1. So as far as the atom is concerned, the nucleus is going to have most of the mass, but the electron cloud is responsible for all the volume. So again, like we said, protons and neutrons are heavy. They make up the nucleus, so it's a heavy nucleus. The electrons are light, but they're very spread out and take up a huge volume when compared to the nucleus. So here's an example. It says, if this positive particle below were the proton in a hydrogen atom, it would take a screen 1 mile across to display the electron's orbit. So the nearest electron would either be half a mile to the left or half a mile to the right. Atomic number. The periodic table is organized in a way of increasing atomic number. The atomic number is the whole number that is unique for each element on the periodic table. The atomic number defines the element. For example, if the atomic number is 6, then the element is carbon. If the atomic number is not 6, then the element is not carbon. The atomic number represents a couple of things. First of all, it'll tell you the number of protons in one atom of that element. If it's a neutral atom, it will also represent the number of electrons. So as long as this atom is neutral, protons equal electrons. So, for example, for sodium. The sodium atom, we can look it up on our periodic table. When it has an atomic number of 11, we know that the protons in a sodium atom will be 11, and the number of electrons will also be 11. So these should be the same. For magnesium, it has an atomic number of 12, so 12 electrons, 12 protons. Sulfur, same thing. 16 is the atomic number, so 16 protons, 16 electrons, etc., as long as it's a neutral atom. So what if the number of electrons and the protons are not equal? This is called something different. It's called an ion. And an ion is an atom or a molecule in which the total number of electrons is not equal to the total number of protons, giving the atom a net positive or net negative electrical charge. So here's some examples. Some positive ions. You can have sodium plus, which is really sodium plus 1. We just don't write the 1. Where this sodium ion has 11 protons and 10 electrons. So this should make sense to you. If we have 11 protons, this is 11 positive charges. And if we have 10 electrons, then this is 10 negative charges. So overall, we have a charge of +1, right? Hence the +1 for the sodium atom. Another example is beryllium, in which there are 4 protons and only 2 electrons. So the overall charge is a +2. So we have positive ions, but we can also have negative ions, like the chloride ion. What if we had 17 protons? Well, that's 17 positive charges, but 18 negative charges from the electrons. Well, the overall charge here would be -1, hence the charge on the ion. So realize, if it's neutral, protons and electrons will be equal, but if it's an ion, they will not be. There's also something called an isotope. So isotopes are 2 or more forms of the same element, but what's different is the number of neutrons. So ions differ in the number of electrons, where neutrons are going to be different in isotopes. Hydrogen, for example, has 3 different isotopes. One form of hydrogen has 0 neutrons. Deuterium has 1 neutron, and tritium has 2 neutrons. As you can see in the picture, though, this is neutral because they each have 1 proton and 1 electron. So again, isotopes differ in the number of neutrons only. Mass number. So we get the mass number by adding together the number of protons and neutrons. If I said I have an atom and it has 6 protons and 6 neutrons, we add them together and that is a mass number of 12. In order to show the difference in isotopes, we can use isotope notation. Here are the isotope notations for the 3 carbon isotopes. So we can write out the name dash the mass number, or this form gives a little more information. On top it has the mass number, but on bottom it has the atomic number. And it's not really necessary to write out the atomic number, because if I know this is carbon, because it's giving me the symbol C, I can just look it up on the periodic table. But realize this is an isotope notation form. I want to emphasize in this moment that in isotope notation, mass numbers on top, atomic numbers on bottom. Please do not confuse this with what you're seeing on the periodic table. So this is what you would see on the periodic table for carbon. You see the symbol C. On top, though, you're going to have the atomic number, which is 6. And on bottom, you have something called the average atomic mass. And we're going to talk about average atomic mass a little bit later and how to calculate. But average atomic mass is different than mass number. And I'll explain to you why in a moment. But please don't get these confused. So I can get calculations where you need to figure out the number of protons, neutrons, and electrons in different forms of different atoms. So a way to keep all of that together and to remember those calculations is to use this mnemonic, APE MAN. It's corny, I realize that, but it is really helpful. So APE MAN, what does it mean? Your atomic number is going to be equal to the number of protons, which is equal to the number of electrons, as long as it's a neutral atom. Man is mass number minus atomic number equals the number of neutrons. Especially if you have this written out in isotope notation, it's really helpful because mass number's on top, atomic number's on bottom. So when you subtract, you automatically get the number of neutrons. So this form of carbon, carbon 14, would have 8 neutrons. Let's try another one. How many protons, electrons, and neutrons are in each isotope of carbon below? Okay, well, I can find carbon on my periodic table. Here it is. And I know its atomic number is 6. So this means 6 protons and 6 electrons for neutral carbon. So all these isotopes of carbon have 6 protons and 6 electrons. They only differ in the number of neutrons. Well, how do I figure that out? I take the mass number minus the atomic number, and it's going to give me the number of neutrons. So 12 minus 6 gives me 6 neutrons. 13 minus 6 gives me 7. And 14 minus 6 gives me 8. So it's a very simple calculation. Atomic mass. It represents the average atomic mass of all isotopes of an element. It is found by a weighted average technique taking into account both the abundance of all the isotopes as well as their masses. So you do the same thing. You do a weighted average technique when you calculate your grade in a class. Okay? You wouldn't simply average together a test grade and a daily grade and divide by 2 and get your average for the class, right? That wouldn't make sense. Well, it doesn't make sense because tests are worth more, right? They are weighted more heavily. The same is for calculating average atomic mass. If the isotope is more abundant, then it's more available, and so it's weighted more heavily. And I'll show you that in a moment with a few calculations. It says atomic mass is measured in AMU, which is atomic mass units. 1 AMU is 1.660538 times 10 to the negative 24th grams. The masses of all elements are compared to carbon-12, which is defined as having a mass of exactly 12 AMU. Atomic mass is the number on the periodic table that has several decimal places. So again, on your periodic table, average atomic mass is this bottom number. So let's do an example using the weighted average technique to figure out the average atomic mass of neon. It says neon has 3 isotopes. We have neon 20, which has a mass of 19.992 AMU, and it has an abundance of 90.51%. So most of neon is this form. Neon 21 has a mass of 20.994 AMU and an abundance of 0.27%. Neon 22 has a mass of 21.991 AMU and abundance of 9.22%. What is the average atomic mass of neon? Together the masses of all of these using the weighted technique. So let me show you how. I'm going to start with my first isotope. I have neon 20. And I'm going to take its mass, which is 19.992, and I'm going to multiply it by its abundance. Okay? I'm not going to leave that abundance in percent form. I need to take it out of percent form and put it in decimal form by dividing by 100 or moving my decimal 2 to the left. So I'm going to multiply it by 0.9051. Okay? Then I'm going to take my next one, which is neon 21. I'm going to do the same exact thing. I am going to take its mass, and I'm going to multiply it by its abundance, again moving the decimal 2 to the left or dividing by 100. So by 0.0027. This is very, very rare. You're not going to find this type of neon very often. And then the last one, which is neon 22. Its mass is 21.991 AMU, and its abundance is 9.22%. Divide by 100, and I get 0.0922. Okay, so I'm going to do all this first, and then I'm going to add them together. So using the order of operations, you would always multiply first. And then I'm going to add them together. And this is a weighted average technique. It's pretty simple. And when you do this, you can always check yourself because you get the number on the bottom of the symbol on the periodic table. So neon has an average atomic mass of 20.18. And by doing my calculations, they come out to be equal. I hope you enjoyed this lesson today. I look forward to seeing you in class tomorrow. Have a good evening.